Welcome back to the deep dive. Today, we're getting into something pretty specialized, looking at a single piece of medical technology that is, well, both incredibly simple and surprisingly complex.
It really is. And our source material for this is just perfect. We're pulling from excerpts of Dr. Raju's YouTube series.
Oh, that's a great source.
It's fantastic. Specifically, his video on the hot biopsy forceps. He does such a good job breaking down not just what it does, but, the critical differences in how you use it.
And that's really our mission today. We want to unpack this one instrument, how it works for both diagnostics and for actual treatment. And maybe more importantly, why a tiny change in an electrical setting can have massive consequences.
That's the whole story. You have what looks like a standard tool, but you add this one element, electricity, and it just radically changes its utility and its risks.
So we're talking about the hot biopsy forceps, or HBF, and at first glance, it looks like any other biopsy tool, right? But it's got this power upgrade.
Exactly. It's a great example of a small tweak making a huge difference. A normal or cold biopsy just snips a tiny sample. That's it.
It's just for diagnosis.
Right. But the hot technique, it lets you cut and control bleeding at the same time. So it's not just for sampling, it's for actually removing small polyps or, residual tissue.
So you get the mechanical grasp, but it's amplified with this controllable energy. It's a sampler and a removal tool all in one.
Precisely. And that brings us right to the basics, the anatomy and core function of the thing. Visually, like we said, it looks almost the same as its standard counterpart. It's designed to go through the working channel of an endoscope.
But the key is that little electric connection.
That's the game changer. That one connection gives it this dual capability. You can take a standard biopsy for the lab, or you can activate the current and use the hot function to cut and remove tissue.
Okay, so that electrical part has to introduce some new requirements for the setup. It's not just plugging it in, I assume.
Not at all. The HBF has to connect to an external electrocautery machine or a generator.
And this is where safety becomes a huge deal. You mentioned the grounding pad in your notes. Why is that so non-negotiable?
What? It's absolutely essential. We're dealing with what's usually a monopolar setup. So for the electricity to work, it has to complete a circuit.
A circuit through the patient.
Through the patient, yes. The current flows from the forceps tip through the targeted tissue, and then it needs a safe path back to the machine. That's what the grounding pad is for. It's this large flat pad they'll place on the patient's thigh or back.
So what happens if you don't have that pad, or if it's not working right? Where does the electricity go?
It finds the path of least resistance. And that could be anywhere. It could be another part of the patient's body touching metal on the table.
Oh, wow.
That can cause a burn, a serious thermal injury at a site you never intended. The grounding pad ensures all that current flows back safely without causing any harm. It's really the bedrock of safety for any of these hot procedures.
That puts things in perspective. It's not just about the tool in the doctor's hand, it's about the entire electrical system they've built around the patient.
Exactly.
Okay, so let's move from that macro setup to the micromechanics of actually using it. The sources highlighted something that I found really surprising, a kind of practical hurdle with friction.
Yes, this is a fascinating detail. Mechanically, it operates a bit like a bicycle brake cable. The doctor uses a thumb ring to pull an inner wire that runs the whole length of the instrument.
And that pole closes the little jaws at the end to grab the tissue?
Right. Simple enough. But the problem comes from the path that wire has to take. An endoscope isn't straight. It makes sharp turns inside the body, say in the colon.
So the wire is scraping against the inside of the sheath the whole way.
And once you close those forceps tightly on tissue, that friction spikes. It becomes really difficult to move.
What does that mean in practice, like during the procedure?
It means a few things. First, any kind of fine adjustment or, rotating the tip becomes almost impossible. You lose that smooth control.
And I imagine trying to reopen the jaws if you grab the wrong spot would be difficult too.
Very difficult. It can be a jerky, strenuous movement.
Mm-hmm.
And in a space where you need millimeter-level precision, a jerky movement could tear tissue.
So you really have to get it right the first time.
You do. It completely changes how you approach it. You have to pre-rotate the scope, pre-align everything, and be absolutely sure of your target before you close those jaws. It's not a tool you can finesse once it's engaged.
That's amazing. Such a high-tech procedure being limited by such a basic mechanical problem like friction really underscores the skill involved.
It absolutely does.
This feels like a perfect transition to the real core of this, which is the electrical part. The difference between using cut current versus coagulation current.
This is the most critical choice the operator makes. And we're not just talking about high heat versus low heat. These are fundamentally different types of electrical energy.
So let's start with what's preferred today. What does Dr. Raju's series say is the standard?
The standard, the preferred technique, uses cut current. And the source specifies a setting of around 30 watts.
30 watts of cut current. How is that different from coagulation?
So think of it like this. Cut current is a continuous, high-frequency waveform. It heats the tissue cells so incredibly fast that they basically vaporize.
Creating a clean separation, an incision.
A very clean, very localized incision. It's designed for speed and precision.
And this creates a specific effect, right? The source calls it the J effect.
Yes, the J effect. That's the key term. It refers to that perfectly defined zone of ablation. Because the energy is so fast and focused, the thermal damage is limited to a very, very shallow and predictable area right where you made the cut.
That sounds like exactly what you'd want. Take out the bad tissue, leave the good tissue completely alone.
Precisely. To use an analogy, cut current is like using a laser to trace a perfect line. The energy is intense, but it's narrow. It doesn't spread.
Okay, so what's the alternative? What's coagulation current like?
Coagulation current. That's more like using a wide, blunt torch. It's a slower, lower voltage current that spreads out. It's designed to cook the tissue, to desiccate it, to stop bleeding.
So it's not cutting, it's burning.
In a way, yes. It spreads heat much more widely and penetrates much deeper beneath the surface, and that's where the danger comes in.
Which makes it totally clear why the preference has shifted. You want the laser, not the torch, when you're working inside the thin wall of the gut.
And that's why the older techniques that relied on coagulation current are, for the most part, avoided now, especially for these smaller removals.
Let's really dig into that. Why is that slight difference in current type so huge for patient safety? What are the specific risks of using coagulation?
The fundamental issue with coagulation current is that deep, slow heating. It's designed to stop bleeding, but in doing so, it creates a wide zone of deep tissue damage, subsequent necrosis.
Tissue death. It goes deep into the bowel wall.
Way too deep. And this leads to two huge problems. First, the margin of the injury is a mystery. The operator can't actually see how far that thermal damage has spread.
It's invisible damage.
It is. And because that damage is so deep and so poorly defined, it sets the patient up for serious, delayed complications.
Delayed complications.
Yes, things that don't happen right away. We're talking about a delayed perforation, where that dead tissue just sloughs off days later, leaving a hole in the colon.
That's catastrophic.
It is. Or significant post-polypectomy bleeding that can happen a week later. The immediate result might look fine, but you've basically left a ticking time bomb of damaged tissue.
That is a stark difference. So with coagulation, you're managing this deferred risk.
Constantly. And even made the procedure more complicated. The source notes that with the older technique, to remove even a small, say, 3 or 4 millimeter polyp, you'd often have to do a submucosal injection first.
Where you inject fluid under the polyp to lift it up.
Exactly. You create this fluid cushion to act as a heat sink, to try and protect the deeper layers from that unpredictable heat from the coagulation current. It adds time, complexity.
More steps, more risk.
Right. Whereas the modern cut current technique, because you have that guaranteed shallow J effect, you don't need that cushion for small lesions. You can just safely and efficiently remove them. It's a massive leap forward in both safety and efficiency.
So you're basically swapping a physical safety cushion for an electrical one. The waveform itself is the safety feature.
That's a perfect way to put it. It's precision engineering winning out over brute force. And the direct result is a massive reduction in postoperative risk.
This really shows how medicine is constantly evolving towards, more defined, more localized effects to prevent those delayed dangers.
Subtlety in the setting, massive difference in the outcome. That's really the heart of what the source material is showing us.
Okay, so let's tie this all together for you, the listener. The big takeaway here isn't just the name of the tool, the hot biopsy forceps. It's about understanding the variables.
Right. First, there's that mechanical challenge, the friction, which means the operator has to be deliberate and precise before they even grasp the tissue.
And then the critical part, the electrical setting. It all comes down to choosing the modern, preferred cut current, set around 30 watts, to get that controlled, shallow cut, that J effect.
Which lets you avoid the deep, unpredictable, and frankly dangerous damage that comes with the older coagulation techniques.
When you step back, this one technical preference really speaks to a broader philosophy in medicine today, doesn't it?
It does. It shows how we're always trying to refine our tools to favor localized, predictable effects over widespread, uncontrollable ones. It's all about making sure what we do today doesn't create a bigger problem for the patient next week.
A powerful point. Now, to wrap up, let's leave you with a final provocative thought to chew on, building on that mechanical problem we talked about.
The friction issue.
Exactly. If we know that the friction between the inner wire and the outer sheath is a major operational challenge, making it hard to adjust or reopen the forceps once they're closed,
Mhm.
what kind of breakthrough in, say, material science could solve that? Maybe some new kind of coating or a total redesign of the inside of that sheath that could eliminate that resistance completely while still giving us that perfect localized J effect from the cut current.
That's a great question. You're talking about the biomechanics of materials under extreme stress and curvature. A really fascinating challenge for the next generation of engineers.
Something to think about. Thank you for diving deep with us. We'll see you next time.